Thank you everyone for attending the NF University's webinar series, NF University. Our presenters today are Glenn Wright and Alex Ferguson, and the topic is farm building energy efficiency, retrofits, and heat pumps. Alex Ferguson is a researcher at Natural Resources Canada. Since joining NRCan in 2023, he's led efforts to integrate new envelope and heating technologies into residential buildings. In his work, Alex collects experimental measurements from laboratory testing and from field trials and integrates these into nationwide models of energy, carbon emissions, and affordability. Alex also works closely with colleagues from National Research Council and Codes Canada to integrate these findings into our building codes. Our second presenter, Glenn Wright, and his family grow grains, oilseeds, and pulse crops near Delisle, Saskatchewan. Glenn worked as an engineer for 20 years and recently became a lawyer. Glenn and his family have installed a solar array, heat their home with geothermal energy, recently completed a deep insulation retrofit on their home, and have reduced domestic emissions by more than 50%. Glenn and his family have adopted low input farming practices to reduce reliance on purchased inputs, to reduce greenhouse gas emissions, and to manage risks. So a big thanks and welcome to our two presenters. Alex, please go ahead.
Thank you, Darren. So first off, I just want to take a moment and acknowledge that the lands where I'm giving this presentation here in Ottawa are part of the traditional and unceded territory of the Anishinaabe First Nation. And with that, I'll get going here. So my presentation today will be a bit of an introduction to heat pumps. I'm sure some of you probably have a bit of familiarity with this technology. Some of you might own a heat pump already. Increasingly, they're becoming more and more important and more common in how we heat homes in Canada. And this presentation will serve as a little bit of introduction to the technology, talk about the different types of heat pumps. I'll be giving you a little bit of information about how you can figure out if your home's a good candidate for heat pumps. Talk about what some of those implementation scenarios do look like for you. And then we'll also look at a little bit of the cost of heat pumps. We'll have a look at the capital, the operating costs, and what they mean economically, and talk a little bit about what they mean from an emission standpoint as well. So to begin, I just want to talk a little bit about what a heat pump actually is. And if you're not familiar with it, it's a type of very efficient heating and cooling appliances that you can use for your home. And if you're familiar with a furnace efficiency or looking at the nameplate rating of a furnace or a boiler, you might be familiar with efficiencies that might be measured around 90, 95, 98%, and that sounds pretty good. Heat pumps are significantly more efficient than that. And so when we talk about heat pump performance, we talk about efficiencies that are measured around 1.8 or 180% to 190%, sometimes even as high as 270% or 300%. And in fact, because we're talking about percentages greater than 100%, we often use a terminology called COP, or coefficient of performance, to refer to that. Kind of sounds like magic that a heat pump can achieve an efficiency greater than 100%. And it's certainly a very great way to heat your home. It's not actually magic. It's using the same technology that you find in your air conditioner or in your refrigerator. And it works by drawing extra energy from the ambient space, from colder temperatures, and then upgrading it and moving it inside your space. That's why we call it a heat pump. And you can think of it as just like a pump can pump water up a hill. A heat pump can pump heat from cold temperature up to warm temperatures. And one of the key ideas that is really important to understand about heat pumps is they also include a backup heating system as well. And that helps ensure that even when this technology, as it gets really, really cold outside, that your home is going to stay comfortable and warm through that period. There's a couple common types of heat pumps, and it's helpful to understand a little bit about them. So the first one, the most common type of heat pump, is an air source heat pump. And we call it air source because it's drawing its heat from the outdoor space and bringing it into the house. Now, air source heat pumps have been around for a very long time. They historically have not worked particularly well in cold weather, So if you ever heard anybody say that a heat pump is not a good choice for Canada, that it can't keep up in a Canadian winter, those folks are probably talking about an air source heat pump. There's another type of heat pump called a ground source heat pump, and that works very differently. By instead of drawing heat from the air, it draws heat from below or from below the earth. And to build a ground source heat pump, we sink wells, we drill wells kind of like you would with a water, and those holes then become a loop by which we can circulate a working fluid to capture heat from the ground and bring it inside the space. Ground source heat pumps are amongst the most efficient ways you can heat your building. They work very well even in the coldest temperatures, but they're also quite expensive. There's another type of heat pump that you're probably starting to see quite a bit more of these days, and that's called a ductless heat pump. And that's a heat pump that can be installed without having a central air or central hydronic distribution system. And it's comprised of two parts. I hope you can see my mouse as I'm gesturing on screen here, but there's an outdoor unit that looks just like an air conditioner. There's an indoor unit that looks like a box that you would see on the inside wall, and they're connected by a chase that sort of allows the heat to move back and forth between these two systems. You may also have heard ductless systems called mini splits or sometimes multi splits. We'll talk a little bit more about what they mean and how they're used in a few moments. There's other types of heat pumps that you should be familiar with. And so the first one we're actually really excited about in Canada is a new class of heat pumps called cold climate heat pumps. And they're like air source heat pumps. They look very similar to air source heat pumps or even like to air conditioners that you might be familiar with, but they have special technology inside of them that allows them to be even more efficient at very, very cold temperatures. So previously we would talk about heat pumps sort of running out of steam at around -5 to -8 degrees Celsius, not being a great choice for many parts of Canada. Cold climate air source heat pumps have no problem running down to -25 or -30 degrees Celsius, and that allows them to be very efficient over the entire period of winter. Another class of heat pump that is becoming increasingly popular called hybrid heat pumps, and these are heat pumps that take the electrical component of a heat pump and combine it with a gas furnace. And this approach makes sense for homes that maybe aren't ready to completely separate or to remove gas heating from their house, or maybe can't access a higher electrical service. We'll talk about that in a minute. But the basic idea is that you use the heat pump when the temperatures are more mild, and then you switch to gas for the gas heating back up as temperatures drop. And we'll have a look at that in a few minutes. Another class of heat pump that you may be starting to hear more about is gas heat pumps. And these are heat pumps that are usually either run off a natural gas engine or using a natural gas absorption heating cycle. And so instead of using electricity as their primary input, the natural gas is the primary input to these systems. Now, these systems typically are not commonly found in North America. Most of the manufacturers that are producing these systems are coming from Europe. And you'll also find that these systems are typically not well sized to typical residential appliances. And you probably will find that they're relatively less common to find trades who are comfortable installing these types of equipment. A couple quick questions. Why would you choose a heat pump? Well, the first thing is in Canada, a heat pump is much cheaper to operate than an oil, propane, or baseboard heating system. So if you're using those systems, you're going to find that the economics of heat pumps are going to save you a lot of money year over year. In fact, we find that their costs are increasingly competitive with natural gas. And in most parts of Canada, that's the cheapest way you can heat. But we're finding that heat pumps are increasingly approaching the operating costs of natural gas. Heat pumps are also going to lower carbon emissions in most parts of Canada as well. So if you're choosing a heat pump, the greenhouse gas impact and the carbon impact of your buildings is going to come down. And another key aspect here is that they're going to be able to provide cooling even in summer homes. And the mini split option, the ductless systems that I've talked about a few moments ago, can be a great option for homes that don't have central air and are finding that as summers get warmer and hotter, that their conditions are less comfortable and they're looking for a means to bring air conditioning into those spaces as well. There's a number of misconceptions about heat pumps, and I think it's valuable to take a moment and go through them. So misconception number one, heat pumps don't work in cold temperatures. That used to be true, but we have lots of new heat pump technologies that can operate down to temperatures to minus 25 degrees Celsius and below. It's important to note that also there's a backup system there. So even if the heat pump, as it starts to run into very cold temperatures and it's not working as efficiently as it normally would in the mild part of the year, heat pumps come with a backup system that helps ensure that your house is going to stay warm, even if the heat pump is unable to keep up with those very cold temperatures. The third misconception is heat pumps are very expensive to operate. And again, if you used an air source heat pump, a conventional air source heat pump in regions that was very cold, you might find that that heat pump was really relying on its electric resistance backup for most of the period of time, and that would be a very expensive way to heat your home. But when you're using a more efficient cold climate air source heat pump, you're going to find that that's going to give you much lower operating costs than oil heating or propane well, and you're going to find that those costs increasingly approach the cost of heating with natural gas. How do we know all this? I've been fortunate to work in a research lab here in Ottawa that's been testing heat pumps for a number of decades now, and we do this in a number of different ways. I have my colleagues in the experimental testing component of our research lab have been buying heat pumps. They've been installing them in a test chamber we have here at Camna Energy Ottawa. That test chamber is a fancy word for a refrigerated shipping container. We put the heat pump in the refrigerated shipping container and run that system down until it's about minus 20, minus 25, minus 30 degrees Celsius. And we're able to carefully measure how much heat is coming off that heat pump can deliver, to know how efficient it is, to know how much capacity it has in cold weather. We also install those same heat pumps in test homes and in field trials and monitor their performance in real world conditions to make sure that when we're making these recommendations that these systems will work. And if you put one in your house, you'll find that it's able to deliver that performance and that heat that you're depending on. Um, but that doesn't mean a heat pump is necessarily going to be right for you. And so there's a number of factors that are going to help you determine if a heat pump is going to work in your home. The best resource I can give you to determine if a heat pump is going to make sense in the application for where you are and the house you have is to go out and get an EnerGuide evaluation. So if you're not familiar with the service, Natural Resources Canada has worked with partners across the country to offer a home EnerGuide evaluation service where a professional will come into your home, take a number of measurements, inspect the insulation, the windows in your home, do a blower door test, and create a very careful, very accurate picture of how efficient your home is. And they're going to be able to tell you if your home is a good candidate for a heat pump. That decision is going to probably depend on three primary factors. The first primary factor is the climate and loads. So how cold is it? How cold are your winters? And how well insulated is your home? And what are the resulting heating loads that you're going to have? Another key factor is the electric service in your home. And then the third key factor is the distribution system that your home uses to supply heat. And we'll look at those sort of one by one. So the first one is climate and loads. And if it is important to note that even the most efficient heat pumps we have, they are less effective in colder weather. So as the temperature drops, the efficiency of the heat pump comes down a little bit, the capacity of the heat pump diminishes, and it's going to depend more and more on the backup heating system that's there. So the heat pump system that you choose has to reflect the climate that it's in. And if you're in colder parts of Canada, you're going to be looking at a higher efficiency heat pump, say a cold climate heat pump or a ground source heat pump, which is going to help keep up with that super cold weather. The other key factor is the level of insulation in the house or the building that you're working in. And so better insulated and better sealed homes and buildings are also better candidates for heat pumps because they have lowered loads. And so one thing that you can imagine is the cold weather increases the loads in your building. Insulation and air sealing help bring those loads back down. So the efficiency measures that we talk about reduce the number of hours that the heat pump is going to have to rely on its backup. And it's going to help ensure that it stays within the capacity it can operate. If you're lucky enough to live in a new net zero ready home or a passive house home, you may find that your house doesn't actually need any backup at all because the loads in that home are so low that the heat pump can actually keep up even in the coldest weather. So I've got a little chart here. You'll find it in my presentation. You may want to have a look at this afterwards because it helps explain whether your home is likely to be a heat pump ready home, whether an EnerGuide evaluation is going to help you figure out if that's the case. And so across the top here, we've got a bunch of different climate zones, and I should probably point out to you these are the ASHRAE climate zones for heating and cooling equipment. Not necessarily plant hardiness zones or other definitions that you might be a bit more familiar with. And so the warmest locations in Canada are actually in climate zone 4, and that would be Vancouver Island or Vancouver, BC, with heating degree days of around 3,000 or less than 3,000, I should say. And then if you're in London, Ontario, you'd be in climate zone 5. Montreal, Ottawa, where I live, is climate zone 6. Winnipeg is climate zone 7A. We don't have in many major cities in climate zone 7B and 8, but if you were in Fort McMurray, Alberta, that's where you'd find yourself. Oh, sorry, I skipped ahead there. And so if you're in climate zone 4, you're probably okay with a standard air source heat pump, but as you start to move to climate zone 5 in these colder locations, you're probably going to want to consider a cold climate air source heat pump or a ground source heat pump, because those are the systems that are going to work well in super cold temperatures. Now, if you have the benefit of living in a recently constructed energy efficient home, like a passive house, a net zero home, or even an Energy Star home, your home is quite likely heat pump ready right now. And you have the required insulation, the air sealing that you need to be able to put a heat pump in there and have some confidence it's going to work quite well. If you have a newer home built to code, that's probably good enough in climate zone 4, climate zone 5. As you start to think about climate zone 6, that's where I'd start to recommend that EnerGuide evaluation is going to be a useful tool for you to understand what the loads are in your home and decide if maybe some additional insulation is going to help you make sure that you're heat pump ready. If you have an older home with updated windows, topped up attic insulation, maybe some air sealing, maybe some further insulation improvements, that's going to be heat pump ready in climate zone 4. In climate zone 5 and climate zone 6, the EnerGuide evaluation is just going to help you assure that yes, that home is a good candidate for a heat pump. As you get to climate zone 7A and 7B, I would strongly recommend you you look at an EnerGuide evaluation just to help to make sure that heat pump's going to be a good candidate there. And then if you have an old drafty house, well, you might get away with it in climate zone 4, but anywhere else, I would say an EnerGuide evaluation is a key step to figure out if you're heat pump ready. Let's look at factor number 2. That's the electrical service. Most Canadian homes have 100 amp service, and that's enough for you to run a heat pump and meet all the other requirements in most homes, provided you don't have a jacuzzi or other high electric services there. But it's not enough to run the backup system. So if you're going all electric, you're going to find that 100 amp service is probably not going to be sufficient. And you're going to have to think about either going a hybrid approach, which uses natural gas or propane as your backup, or you're going to have to think about going to a 200 amp service. So just a quick summary here, different types of electric service across the top. Different types of heat pumps at the first. So if you have 200 amp, you're ready to use a central air source heat pump, cold climate air source heat pump, ground source heat pump. That's all good. You can do mini split or multi-split setups with 200 amp. That's all okay. You probably have enough amperage there to run an electric vehicle as well. If you are where most Canadians are, where you have 100 amp service, then you're going to find that the heat pump is not going to be, the heat pump can be installed, but you're going to need to stick with some other oil, gas, propane backup to ensure that when that heat pump is not able to keep up with capacity, that you still have the ability to keep the house warm. And then if you have 60 amp service, which a number of homes or some of our homes still have, you're probably going to find that you're going to need a service upgrade. That the heat pump itself is not going to fit on that panel, and you're going to need to upgrade one way or another. Just one other note I'll offer here is if you're at 100 amp service or you're at 60 amp service and you're contemplating this upgrade, you know, if you're also thinking about an electric vehicle in your future, then that upgrade would likely give you the headroom to be able to charge an electric vehicle as well. The last one, and probably the most complicated decision around all this, has to do with the distribution system. So the way that your home currently takes heat from whatever boiler or furnace or whatever you're using and distributes it into the space is also a really important consideration about whether your home is heat pump ready or not. And so there's three common types of heat distribution in Canada. We have central forced air, which is very common in the western part of Canada, hydronic radiators, which is more common in Quebec and Atlantic Canada, and an electric baseboard, which is very commonly used in Quebec and Atlantic Canada, but also in some parts of BC and some parts of Ontario and in some types of houses as well. So if we go back to our chart here and we think about what the path for each of these is, if you're central forced air, it's relatively easy to take a central forced air system and couple and put a heat pump or attach a heat pump to it. So you're going to find that generally speaking, cold climate air source heat pumps and conventional air source heat pumps, ground source heat pumps and gas hybrid systems are all going to be an option for you. The only consideration that you might get into is what is the size of your ducts? And is it good enough to support heating the whole house with a heat pump? Or do we have to think about only using the heat pump or sizing it mostly for air conditioning and doing heating and other purposes as well? These other options, though, if you have radiant floors with hydronic or baseboard or electric baseboard, you're going to find that it's much harder or much more complicated to take a heat pump and connect it to those types of systems. It is true that we have a technology called air to water heat pumps that can actually provide heat for hydronic heating. But in generally speaking, um, those systems may not be compatible with your hydronic heating system if they're not if your hydronics heating system is not designed to work at very cold temperatures or relatively low heating temperatures, I mean to say. So most hydronic systems are optimized to work around 70 to 90 degrees Celsius input water. Heat pumps are going to work much better in the 45 to 50 degrees Celsius range. If your hydronic system is like an old cast iron baseboard or baseboard convectors, you may find you have to upgrade those to fan coils or some other way to heat. Um, and then if you have electric baseboard, you're going to find there really isn't a heat pump system that can connect to that kind of equipment. So if you're one of those, if you're a household that has a hydronic system or has an electric baseboard system, you're going to be looking at the bottom row of this table, which is the mini split and multi-split option. And in that scenario, you're probably going to keep your radiant system, your electric radiant system, or potentially keep your hydronic system as well. But you're going to install a mini split, an outdoor unit with dedicated heads that will supply heat or cooling to various parts of your house and will work independently of the central heating system. Okay. Let's take a few minutes and talk about the economics of heat pumps. Um, Straight up, heat pumps generally cost more than traditional appliances, traditional heating appliances like furnaces. But and sometimes they have cost. Sorry, let me start that thought again. They generally cost much less to operate than oil furnaces or propane furnaces, and we find that their costs are increasingly lining up with natural gas. Let's look at some of those numbers just so we understand what I'm talking about here. So I've got some illustrative capital costs on the screen here, and I want to begin the conversation around these to say they're indicative. There's lots of reasons why economic pricing is for these systems is in flux right now, much as like there's lots of reasons why the prices in my groceries seem to change week to week and never in my favor. The same is certainly true of heat pumps and mechanical systems. Supply chain disruptions and increased demand for these technologies is definitely affecting prices. But nevertheless, I'm fairly confident to say that these are good indicators of what you ought to expect to pay in most parts of Canada. So if you're going out and replacing your gas furnace and also putting a new air conditioner, you're looking at about $4,000 for the furnace, about $3,500 for the air conditioner, probably about $2,000 in labor. That puts you over a little over $9,000 in your total replacement cost. If you're replacing oil furnaces, things are a bit more expensive. So oil furnaces cost more, and you also have to think about replacing the oil tank itself. Your total cost in that scenario is probably around $12,000 or up to $13,000. If instead you wanted to install a cold climate heat pump, you're probably looking at about $13,000 for the unit itself, give or take. You're probably going to carry about $3,000 of labor on top of that. And then in addition to that, if you also have to replace the electric service, you're going to be looking at about $4,500 in most urban centers. Perhaps that number will be higher in rural locations for an estimated total of about $20,000 or so. So like I said,
Alex,
heat pumps are more expensive. Yes, Darren.
will you be able to finish up in about 2 minutes?
I can finish up in 2 minutes. Yes.
Very good.
But also think about the operating cost here. So when we talk about the price of a gas furnace, or sorry, price of a heat pump in this middle row here, relative to say electric baseboard or oil furnaces, we can see that those heat pumps are going to cost a lot less to operate over the course of a year, and their costs are sort of in the ballpark of gas furnaces. Usually a little bit more expensive, but not significantly so. So if if you've got electric baseboard heating, electric resistance heating, electric furnace, or if you're using an oil furnace, these economic savings are pretty persuasive. You're going to be looking at a couple $1,000s every single year, less to operate the heat pump than to operate these systems. Okay. In terms of carbon reductions, depends on where you are and depends on what you're replacing. You probably expect a heat pump to save 1.5 tons of CO2 per year over a gas furnace. And if you're choosing it over oil, you're probably saving up to 6 tons per year instead of heating your house with oil. And just to put that in reference, that's about the same amount of emissions as from two passenger cars operating on our roads every year. And I think, Darren, that brings me to the end of my presentation. I have a number of resources here that I'd offer for more information. I think the slides will be circulated afterwards, or Darren, you'll pass the links out there. So please do take a look there. If you're looking for more information about how to get a heat pump, how to get an energy evaluation, or what it all means for you. Thank you.
Thanks very much, Alex. I'll turn it over to Glenn Wright now. Glenn, please go ahead.
No, that's fine. I guess basically what I want to talk about here today is my own experience with heat pumps and building efficiency. And this is largely in the context of my own home, but this could certainly all be applied to other farm buildings, particularly shops and barns for livestock. Is just a much larger scale, but everything to do with building efficiency, these are all principles that would apply to those scenarios as well. Let's see here, how come all right, so this is basically what I want to talk about today is building efficiency, and then thermodynamics. I'll give a very brief overview, but don't be afraid. I know thermodynamics sounds frightening to some folks. And then I want to kind of build on what Alex has talked about, what is a heat pump, and then talk specifically about our retrofit. So this slide here, I want to talk about efficiency and how we all want to be warm. And that's kind of why I had mentioned in the previous slide in the overview that this is sort of like the want of a faster horse. So when people were talking about, improvements to personal transportation, 150 years ago, most people when asked just wanted faster horses. And when it comes to heating our buildings, we generally just want to be warm. And usually the first consideration for folks is, I want it to be lower cost. So if you look at this map of Canada here, now this is showing how our primary heating sources by energy. And you can see that natural gas plays a very prominent role from Ontario heading west, but wood is still used in some fairly large quantities across the country. And, wood comes with a whole lot of extra work that goes along with it, splitting wood and firing and so on. But I think that's what really led to the displacement with natural gas, is that it was very low cost and it was very convenient. But what we're moving towards now is we need to recognize that we need to be more efficient. And this is part of our path to getting to net zero. And so just by comparison, I wanted to show the relative size of our existing infrastructure. And so this is just the Saskatchewan context, but what we need to be aware of is that our gas distribution infrastructure in Saskatchewan, the peak demand in terms of energy on that system was achieved on January 6th of this year, and equivalent to electrical consumption, that would be 19 gigawatts. By comparison, our peak electrical load in Saskatchewan was only 3.9 gigawatts. So it's about 5 times the size. There's 5 times more capacity in our natural gas infrastructure to deliver energy. And so this is why we need to think really carefully about how important it is to reduce our energy demands and focus on efficiency, and not just on residential buildings, but on farm buildings and all commercial buildings. Because I think for so much of our history, we focused just on the convenience and the low cost of energy like natural gas, and we haven't really paid attention to how much we could do on the efficiency side of things. So this focus on efficiency, in Saskatchewan at least, in the 1970s, there was around that first oil embargo crunch that led to people to think about energy efficiency. The provincial government tasked the Saskatchewan Research Council with designing and building a solar house appropriate for Saskatchewan. And this led to some work to develop what was later called the Saskatchewan Conservation House. And so they focused on a lot of insulation and a very airtight construction. And one of the fellows who worked on that project was Mr. Harold Orr, who received the Order of Canada for his work. And when I started working on my energy retrofit, he somehow found out about this and actually made the trek out to our house to see us doing this work and gave us some advice. So it's interesting to me, though, that in 1975, I mean, after all this focus on new technology, and by then we'd put men on the moon, we still were only insulating with R7 insulation and R12 in the attic. So our building code today is not much better. It's not certainly at the passive house standard where it should be, in my opinion. And so I'm hoping people like Alex will encourage our code makers to have more ambition to pursue and mandate tighter homes, because we could certainly use a lot less energy. And I've demonstrated that with my own house here. And so in 2008 is when we made the first commitment to go to geothermal energy. We actually removed our natural gas service from the farm and installed a geothermal ground source heat pump, which I'll talk about later. And at the time, we also installed wind turbines to provide us some renewable energy. Those were a failure, unfortunately, and you can talk to me about that after if you want. But we then moved to installing solar PV, and then we did the deep insulation retrofit. So honestly, we did everything backwards from the way we should have done it. We should have focused on our efficiency and done the insulation first. But just to emphasize the efficiency component here, though, I took a baseline in 2007. So with our natural gas heat and our electricity, our total energy use was about 52,000 kilowatt hours for the year. In 2021, after we'd done our insulation retrofit, our house used only 11,800 kilowatt hours, but by then we were also being provided some energy from our solar system and also using some energy for our EVs. So when I subtract that all out, just our home electricity component, so that's still to run all of our lights and cooking and water pumps and our heat, it used 16,000 kilowatt hours. So comparing that number to the 52,000 number, there's a 69% energy reduction. And even when I think about transitioning our lifestyle to use electric cars, so now not using any gasoline, our home at 11,800 kilowatt hours in 2021 is still less than the electricity that we used in 2007. So my point of all of this is that by focusing on efficiency, we can still maintain our lifestyle. There's a lot of low-hanging fruit in the realm of saving energy that we really haven't focused on. So now the thermodynamics lesson. I don't know how many of you are scared off, but this is a scene from the Back to the Future Part 3 movie. It's one of my favorite movie series, Back to the Future. I mean, Christopher Lloyd and I mean, he's just fantastic in that movie, and Michael J. Fox. So this scene is from Back to the Future Part 3. He's running this large contraption, and they're turning a bunch of valves and a bunch of noise, and it produces ice. And so there is some period correctness to this. Refrigeration was invented in the middle of the 1800s. And so this is period set in the plot in 1885. But really, what we have learned is that energy transfer by heat happens because of temperature differences. This is the thermodynamics lesson. So it's intuitive to many of us. You would think that hot objects transfer heat to cold objects. And that happens by three modes of transfer, either conduction, convection, or radiation. Now, primarily in homes, our heat is lost through conduction or just outright air leakage. And so that's a mass transfer process. So that's why we have to focus on tightening the home to minimize air leakage and putting better insulation in. But something Alex mentioned as well is that heat transfer spontaneously or naturally occurs always in one direction, going from hot objects to cold objects. And so that's what brings us to heat pumps. A heat pump, as Alex mentioned, is something that goes against that natural gradient and instead reverses it to flow heat or take heat energy from colder objects and move it to hotter objects. So it's transferring or pumping that energy from a cold place to a warm one. But as he mentioned, the advantage here is that you can get greater than 100% efficiency because you're putting energy in to do the transfer, but you're getting often a bunch of free energy from that cold object. And these heat pumps have been invented and around for a very, very long time. We've all had refrigeration for probably at least 70, if not 100 years in many homes, but you see heat pumps in your house in places you wouldn't think. So the air conditioner, certainly, chest freezers, refrigerators, but also if you have a dehumidifier. And the air conditioning in your car operates in exactly the same way. So most of these are based on the vapor compression cycle, which I won't go into here, but this is basically how the heat pumps are primarily operating, at least any electrically driven ones. So what Alex also mentioned, though, is that the heating efficiency or the heat pump efficiency greatly depends on the temperature. So if you can understand that a very close temperature difference between two objects, it doesn't take as much energy to transfer the heat. But if you've got one object at -40 Celsius, you're trying to boil water, that's a very large temperature difference. You're going to have to use a lot more energy to transfer heat from the cold object to the warm object. And this is the coefficient of performance that Alex talked about. And so for my house with my ground source heat pump, generally my coefficient of performance is around 3, which means that for every 1 unit of electrical energy I put in, I can get some free units of energy from the ground. So 2 free units from the ground and 1 I put in gives me the total of 3. That's that 300% efficiency. So the picture on the left is really what my house has. It's got a system set up like that, and we'll show some more pictures here later. But what I wanted to emphasize here, this is now just a snapshot of the technical data on a unit very similar to the one that's in my house. And so if you can see my mouse here, this EWT, this is the entering water temperature. So this is from your water ground source loop. My house typically sees entering water temperatures between 30 and 40 degrees Fahrenheit. But the heating capacity of your unit, that's this column here, this drops off dramatically. So when you're at the very low temperatures, you've only got 45,000 BTU of heating capacity for this unit. Whereas if you're pulling heat from a warmer source down here, you're going to have around 60,000 BTUs. So this is the trap or what you have to carefully look at when you're sizing your unit, because if it isn't sized correctly, as the temperature gets colder and colder from your source and it's cold outside and you need more and more heat, you can get yourself into a trap where you quickly realize your unit doesn't have enough capacity. The other thing I wanted to point out here, though, is again, as the temperatures differences widen at this colder temperature, you've got lower coefficients of performance than you would if you're pulling heat from a higher temperature. So this now is just new marketing information. These are new models you can buy to replace the one that would be in my house. Mine being a 2008, I couldn't find a picture of that anymore on the internet, but this would be exactly what I have to replace mine with if it was to fail and need to be replaced with a new unit. So this does 3 things. It does forced air heating and cooling, so air conditioning and heating. And so this is the intake plenum. This is where your air would enter. And so there's a large filter here. And Alex mentioned that your ducting has to be sized. So often with a natural gas forced air heating unit, you have smaller ducts because you have hotter air being circulated throughout the house. So these have larger air ducts usually because they move more air because it's a lower temperature heat supply. So to move the same amount of energy with lower temperatures, you have to move more volume. And then my unit is a combination unit. It also can do radiant in-floor heat. And then it also does domestic hot water assist. So this now is a picture of my unit in my house. This is the same unit here. Here's the ducting, that large cold air return ducting attached to it. And so this combination unit is doing 2 things. It's heating the air to the house. So this is your forced air unit, but it's also heating radiant in-floor heat. So hydronic heating in my floor. And then the domestic hot water is shown here. And these 2 lines here are where your ground source heat loop would be coming from. And now Alex talked about the backup, all of these units having backup supplies. So this is a zoom in on the tag on my unit, and it shows here, this is the electro module. So it's an electric resistive heating element inside the plenum, and it's a 9.6 kilowatt capacity. And so it draws 40 amps and needs a 50 amp breaker. So this is why Alex was talking about the electrical service in your house perhaps not being large enough to accommodate both the geothermal system and the electric backup. Now, since I did the deep insulation retrofit on my house, I've actually just turned the breaker off to my backup. I haven't used the electric backup for our system for about 4 years now. And finally, this is just looking the opposite direction from where I was taking the picture of our unit before. So this is the pump. There's an expansion tank in here and pump. This is what pumps the water. There's 2 little pumps mounted on the side. And so this is what pumps the working fluid, which is actually propylene glycol and water, out to our ground source heat loops. And so there are 5 wells that are drilled, and I'll show pictures of that later. But so the heat water goes out to the wells and then comes back in and goes through the geothermal unit. It only takes out about 4 degrees of heat. So it moves a fairly large volume of water, but has a very low temperature difference. And the rest of this stuff here, this water heater is actually a storage tank for my hydronic floor heating system. And then the pump and this expansion tank is all to do with the in-floor heat. So this is just a picture showing the 5 loops coming into the house. So one side is supply and one side is return. These are cold coming in, at 35 to 38 degrees Fahrenheit. And so you can get condensation forming on these and water dripping off. So that's why this is all wrapped in insulation to try and minimize the amount of condensate that would drip off. And the other thing I should mention about building efficiency, we don't spend a lot of time on this, but about a third of all your energy lost in most homes is just due to air leakage. So this is why we tighten homes up so much, and this is why we add heat recovery ventilators. So that's what this device here is. It's not tied to the geothermal or related to it at all, but this is managing the indoor air, and anytime we lose or exhaust air, we want to condition the incoming fresh air and preheat it with energy that would be in our exhaust air. So that's what these heat recovery ventilators do. And these could be used in industrial settings or commercial settings as well, just on a larger scale. So now this is some pictures of the installation. This is a drilling rig that was brought in to drill the 5 4-inch holes for our ground source loops. And this was in August of 2008. So I contracted this out. And then once the loops were grouted into the ground, then we had a backhoe come and dig this trench and pulled all the loops together. So there was 5 660-foot loops of 3/4-inch poly pipe that were laid into this trench and then backfilled. Now, because our house is a retrofit, we ended up having to daylight these pipes and bring them in above grade. I actually used an old window here, and I just framed this in and precast some 4-inch access holes, ABS pipe, to allow all the tubing to flow through there. But I think if you were doing a new build, you might actually consider putting the pipes much lower into the ground and come through, close to the bottom of your basement so that you'd have all that insulation of the earth above. And so this is just showing how this here is a loop. If you can see the mouse here, this is a loop, one of the wells that was drilled. And so while we were waiting, and we had to trench in or build the trench that connected to all these loops and then lay the tubing in and run it up to the house. And so this now is a picture 10 years later. This is part of my insulation retrofit. We exposed all of this. So we had run the house for 10 years heating with our geothermal system. And we did find that when it got colder than about -32, that our backup heat would turn on, just because we just didn't have enough capacity in our geothermal system for the size of space we were heating. And it's partly due to our house being so poorly insulated and so drafty. And so we excavated around here to try and install some insulation, which I'll show later, but we had also dug about 2 feet down and put some styrofoam over top of where the geothermal pipes, the ground source loop, came into the house. So this is where the water comes in and goes out, these 2 pipes. So this is showing then the work we were doing to insulate. So this is adding 6 inches of styrofoam insulation. We dug down about 6 feet deep We couldn't dig much further just because we didn't have room to manage the spoil pile for the excavation. So I enlisted the slave labor of my children. So we did a learning process here to learn what it was to how houses are built and how to do renovations and insulation retrofits. And like I said, we were very thankful that Harold Orr came out twice actually to look at what we were doing here, gave us some advice. So once we had all the insulation on the foundation, we did this in 2 phases. So this was done in 2018 in the summer, and then we just backfilled the dirt. And then in 2019, we did the stuff above grade. So this is just a drawing I made that I submitted to Municode when we were doing the permitting application for this retrofit project. So our original house here we moved in 2004. So the previous owners had an attached garage, but they had converted this attached garage to a living space and then built another attached garage over here. So this attached garage had no ducting for the forced air heating. So we had to add in-floor heat here. It was originally heated with a natural gas fireplace when we moved in, but there was a whole host of problems I won't go into, and we wanted to get rid of all the natural gas, so we elected to go to hydronic heating in this area. But this insulation retrofit now, we ended up stripping the siding and the soffits and fascia, and built an additional 12-inch thick wall and installed a new vapor barrier around this whole area of the house to tighten it up and triple the amount of insulation on the walls. And we did add some more insulation to the ceiling as well. But this essentially shows what we started with to start the phase 2 of the project, doing the exterior walls. This is the backfilled below grade insulation. And I'll just quickly go through a few pictures. We actually needed to upgrade our service as well. I call it an upgrade, but we were actually downgrading. We had 2 200 amp services at this house, but that meant 2 basic charges, 2 separate bills, and I wanted to reduce the cost. So we wanted to eliminate all this stuff here to do with these 2 meters, which is here, and go to 1 meter. And we also went away from the overhead service to a below ground service. So here's part of the, I guess, progress insulation being added to this wall, and we're just starting on this wall. So the new vapor barrier installed. Progressing here, we're building these frame that is hung off of the truss tails and tied into the existing wall, and then we're adding insulation here. And these are just pictures I'm trying to go through to show how the work progressed. So this is now at the front side of the house, but you can see that the window wells are now 16, 17 inches deep. So the windows were mounted on the exterior, and this is all filled with insulation, and we had the original 2x6 insulation as well. So it's a very well insulated wall now. And here you can see the 2x4s hung off the truss tails, and these struts are actually tied into the studs in the inside wall. So this, I won't go through this in detail, but this is, again, part of what I submitted to do the permit application for the retrofit. So this is the insulation added to the foundation, and there's kind of this frost barrier piece I added. Since I couldn't go down further than 6 feet because of the spoil pile, we decided to add some more insulation at the toe to make the pathway for conduction longer. And then this is just what we did on the above grade, which you can see in the pictures. But essentially what we've done here is we've reduced the amount of electrical load and amount of work our geothermal system has to do. So we save enough electricity now to drive about 27,000 kilometers per year in our electric cars. Now, I only got my one last slide here is this one. It's about my wisdom born of pain. So again, like I mentioned, I did everything backwards. We started with doing geothermal before we did any insulation, and really, this is why that investigation or the audit from the EnerGuide Homes program is so valuable, and getting a blower door test and looking for the lowest hanging fruit. So insulate and tighten your house first. When you do get a geothermal system, though, I would recommend that you equip the heat pump with a soft start. So our electric motor for our compressor does not have a soft start. Whenever it cuts in or the thermostat calls for heat, it starts with a pretty loud bang, and you can hear it throughout the house. So it's a nice option to get one where it ramps up the compressor more slowly, and then you won't hear it. So do look for that. The control system for this is something you should pay a lot of attention to, because many geothermal systems I've seen, including ours, it was trying to run the backup system more often than it should. And it's largely because I think the control systems you buy, most thermostats, are all set up for natural gas, high quality heat sources that can heat the house quickly. And for a geothermal system with lower grade heat, it takes longer to ramp the house up. And so it was actually trying to run the backup system whenever we just wanted to have the programmable thermostat set for low temperatures at night and high temperature during the day. The passive house construction that I was mentioning, that really should be codified, it should be mandatory. It's actually about the same cost as typical construction. It's just what more you spend on insulation and a tighter construction, you have to spend less than on your HVAC system because you don't need as large of a system. And then finally, I would say just make sure, as I mentioned earlier, the cold piping for a ground source system can have sweating, condensation coming off it, so you need to manage that. And then with respect to anything you want to do with building a solar system, I would recommend building the biggest system possible, because you'll always find that there's likely more uses for that energy than you anticipated. And I would say getting solar is certainly a gateway drug to getting an electric vehicle. So subject to any questions, I think that's all I have for you today. So thanks so much for having us.
Thanks very much, Glenn. Thanks very much, Alex.